Four charges of equal magnitude are placed on the corners of a square as shown in the diagram below, where Q is positive. Three empty points are designated on the diagram, P, S, and T. The dashed lines are drawn so they pass through the center of the square and through the center of each side. Okay, so we want to consider the following statements about this situation. All right. A positive charge placed at point P is in the center, will raise the potential energy of the system charge. Okay, so what we're going to do is we take a positive charge, positive, place it right there, and we want to look at how this affects the total energy of the system. So the energy of the system is basically built up by adding each individual charge. So if we look at this as like 1, 2, 3, 4, we bring in charge 1 first, all the others are absent. It doesn't actually change any energy because it's not working against any electric field. And so the idea here is voltage is negative electric field dr path. And so you have a potential, which is going to be related to potential energy. A lot of times people use U. I use E subscript P. It's all the same. Charge times voltage. So if you have a voltage, you have another charge, then you're going to have some energy. But this implies that you're going to have voltage due to one charge due to another charge. So you really need two charges to have energy. One charge by itself isn't going to do anything because it doesn't have an electrical field to work against. So we add a second charge, that's going to create some energy because it works against the electric field created by the first charge. We bring in number 3, it's now working against 1 and 2, so that's going to be some more energy. And then 4, when we bring that in, it's going to work against 1, 2, 3, and 4. And so that's the idea of how we're building up energy here. So the idea then is if we take another charge and we put it at point P, how does this affect the energy? And the idea, what we're going to work with here is we're going to use the idea of Q equals potential energy. So, or more specifically, I'm going to say that Q V, delta V, because it's always at delta. In this case, this delta is between infinity and point P. We assume that the potential at infinity is 0. And so really, we could also kind of sort of write this as Q times voltage at point P. So that is going to give us the change in potential energy. So some people would use U, I use E subscript P. And this Q plus is this positive charge that we added right there. Right, so now the question is, this V, delta V total, is going to be V1 plus V2 plus V3 plus V4. And again, these are all really deltas because they're compared to infinity, but you get the idea, so I'm not going to belabor the point. So V1 is going to be, since it's a point charge, K Q1 over R, where R is the distance from the point. In this case, it's going to be right there. I'm going to call that R. And so now, the nice thing about voltage is that it's a scalar, not a vector. So we don't even have to have a direction with this. So when we do this, we have V total at point P is going to be, I'm going to factor out the K, and these are all R's. So I'm going to factor out the R's for each of these. I'm going to have K over R times Q1, which is going to be positive Q, plus Q2, which is negative Q, plus Q3, which is again negative Q, plus Q4, which is positive Q. These add all up to 0. So the voltage at point P is 0, or more specifically, the difference in voltage between point P and infinity is 0. And so the change in potential energy, when we add a point charge there, change in potential energy is going to be Q delta V, in which case the change in energy is going to be 0 because the change in voltage delta V is 0 because all of these add up to 0. So that's a big concept that's kind of threw out there. The voltage at point P with respect to infinity is 0. Therefore, putting another point there is not going to change the energy system. Thinking of this from a point of view of voltage as bringing a charge from infinity to where we're looking at, this point V equals negative E dr. We took this positive charge, brought it from infinity, brought it down this way. What would happen is it would be repelled by this charge right here, this Q1, this would be force 1, pushing it up that way. But force Q, negative Q, would be this way. So it would be attracted to the negative Q, repelled by the positive Q, and it would have a net force going this direction as we're pulling it from infinity down. So, and you might be like, well, what if we chose a different direction? It doesn't matter because this is a conservative force, path independent. So we can choose any path we want. This one's easiest because things cancel out. The direction of motion is down. The force is to the right. This is a dot product between vectors. Dot product is how parallel two vectors are. Since r in this case is perpendicular to the force, force is q times e dot dx. That's, yes. I think so. Work equals force dx. Yes. Integral. Force equals QE. Yep. So the Q should probably be inside, pulled it out. Long story short, force is basically equivalent to electric field here, perpendicular, therefore not parallel, i.e. the dot product is 0. I know, I said that in the most complicated way possible, but I think it is worthwhile thinking of it in those terms. All right, so now that we've answered a really simple question in the most complicated way possible and shown that a positive charge placed at point P will in fact not raise the potential energy because it'll have 0 effect on the potential energy. And that has to do with the symmetry here, and then the change of potential energy is QV, and then V equals 0. Okay. Number 2, positive charge placed at R will not change the potential energy. So we're looking at R. Positive R will not change the potential energy of the system. Maybe. So this one might be a little bit more nuanced. I'm gonna do the exact same idea. So I'm gonna say change in potential energy equals Q. This is a positive or negative? Positive charge we have, delta V, and then we want to find what delta V is. So delta V here, it's still going to be the idea of we're going to do 1, 2, 3, 4. We're going to have K Q, so we're still going to use the idea of KQ1 over R1 plus KQ2 over R2 plus KQ3 over R3 plus KQ4 over R4. I'm going to say, and this is largely guessing based on the picture, I think we could probably do this more formally, but we don't need to. This distance right here, I'm going to call 3r. I'm going to call this distance 1r. And therefore, r1 is just going to be this triangle like this. r, this is square root of 2r. So r1 equals square root of 2r. r3, very similar triangle, except it's going to be 1, 2, 3. Oh, we'll do r4. R4, the one down here, so 3 by 3. So 3 squared is 9. 9 plus 9 is 18, so it's going to be square root of 18r. Then we're going to look at R2 and R3. R2, the distance, since they're symmetrical, they're going to be the same, just different direction, but since scalar, doesn't matter. We're going to have triangle looks like this. So it's going to be 1r over here, 3r over here, 3r squared, 1r squared. That gives us r2 equals r3, which equals square root of 10r, Pythagorean theorem. And so when we add these together, we get delta V is k q, because they're all the same magnitude. R1 is going to be 1 over, or square root of 2, 1 over square root of 2, r. And then we're going to have r2 and r3, but we're going to have two of them, so I'm going to multiply by 2. And that's going to be over square root of 10. Then we'll plus 1 over square root of 18. And we can pull this r out over here. And long story short, this is only going to equal 0 if this portion right here equals 0. And I don't think it does, but I'm going to throw in a calculator anyway. 1 over square root of 2 minus 2 over square root of 10 plus 1 over square root of 18, and I get a mess. Yes, approximately 0.31, which is specifically positive, but not negative, or not 0. So a positive charge placed will not change the potential energy. Since this is non-zero, that means there is a delta V, a difference in potential, so it will change the potential energy. All right, so then a negative charge placed at point S will not change the potential energy of the system. All right, so we're going to go with the exact same concept here, and the idea here is this R and this R are the same, the charges are the same, but the signs are negative, so the delta V from 1 and 2 will be 0. They cancel each other out because we're looking at V equals KQ over R. The R's are the same, the K's are the same, the Q's are opposite, so when we add them, 0. And the R's, even though they're a different direction, they are the same length, so that's fine because they're scalars. And now this R, I'll call this R2, I should call it R3 and R4. R3 and R4 are the same. Magnitudes are equal and opposite, so those will again cancel. So a negative charge at point S, the sign of the charge in this case doesn't matter because this equals 0. Because the idea is will not change means that change in energy potential equals 0. So it doesn't matter if it's a positive 0 or a negative 0. It's both considered 0. So a negative charge or a positive charge placed at point S will not change the potential energy of the system because the potential energy at point S is 0. Therefore, for the same reason that 1 was false, 3 is true. So to kind of backtrack what we did real quick, I know, super complicated, went way deeper than I should have for a lot of those. The concept we're going for this one is energy potential equals KQ over R. This is a scalar, and this is also written as, this is just voltage, times Q. So we have our positive or negative test charge that we're adding, and this is the positive test charge we're adding times the change in voltage, which is just the individual voltages all added up, which is simple to add up because they're scalars, not vectors. And we just took this concept and we leveraged it down and got some answers. So I hope that helped. See you next time.